is an example problem. Okay, a simple problem where you'll see how to apply these formulas. Okay, this is sigma y equals 36 KSI. Okay, this KSI is kilopound per square inch, which is also same as 1000 pound force per inch square. So that's a unit in the foot pound inch framework, the inch pound, sorry, IPS, inch pound second. So what's going on here is this beam is loaded by moment m, and here this is the y direction. So a steel bar of dimensions 0.8 times 2.5 is subject to a moment m as shown. Find m that causes the bar to yield, given that sigma yield is 36 KSI. So again, we need to figure out what's the relation between m and sigma y in order to solve for m, right? And that's something we wrote down earlier. M divided by I equals sigma divided by y. Right? I ignored the E divided by R because we don't need it in this problem. Okay, now, as I said, if you have a bar and it's subject to a moment as shown, then you will see that there will be maximum tension in the bottommost layer and maximum compression in the topmost layer. So there's another way of writing this. This is sigma max and sigma min, right? And negative here, and it's positive here. In fact, sigma max is actually equal to sigma min. It has the same magnitude, but with a negative sign. So that's the stress distribution. It's always 0 on the neutral axis and increases to a maximum value on the edges where this y is maximum. So if you put y equals 0, for example, or maybe better way to write this is, let's write this as sigma equals my divided by I. Okay, so sigma reaches a maximum value when y reaches a maximum value, and sigma is 0 when y equals 0. So you can see that from that expression. Okay, so now what we are told here is the given sigma is sigma y, m is unknown, y, where will it fail? Where it will fail where the stress is maximum. In this case, the stress is maximum at the top surface, which is in this case half the height. So 2.5 divided by 2. And then the inertia for this section is 1/12 the breadth, which is 0.8 times the height cube. Okay, so here I'm really solving for m, so I need to move things around. So m equals, I messed it up. Okay. Okay, so m equals sigma y, which I'll sub in now. It's 36 KSI, and 36 KSI, I can keep it as it is, or I can convert it whatever you prefer. Let me just keep it as 36 KSI. Okay, and I'm going to move things around. So I would have 1 divided by 12 times 0.8 times 2.5 cube. And then this 2.5 divided by 2 goes down. in the numerator, in the denominator. And so that's what we get. If you simplify that, you get 30, and the units for moment in the IPS system here is kip inch. Okay, so what's kip inch? Kip is kilo pound inch. Kilo pound is, again, like the previous one, 1000 lbf. So that's kilo pound. And then inch is to give it the effect of a moment. And moment is force times distance. And distance units is inch in IPS. Why did we divide 2.5 by 2? Okay, so So 2.5 divided by 2 is basically the distance y. This is y. And y is the distance from the neutral axis. This is y equals 0. This is y equals h divided by 2. This you might say is y equals minus h divided by 2. And that's why we divided by 2. Okay, by the way, if you type something in the chat, it's not recorded by the software. So your name won't show up in the recording. That's a good thing. Anything about Zoom doesn't quite get recorded. Only so these controls, for example, they don't get recorded. It's only the screen which is captured minus anything with Zoom. So if you have questions, people who are online, feel free to ask questions. It will not show up in the recording. So let's do another problem. This time we've changed the geometry. It's a annular geometry. There is a hole of rectangular cross section. Okay, a rectangular tube has an ultimate strength of 60 ksi and dimensions as shown. Find A, bending moment such that the factor of safety is 3, and B, radius of curvature. Now, radius of curvature is 1 divided by R. And assume that E is 10.6 times 10 raised to 6 psi. Okay, so what we'll do is we'll first write the formula which helps us to solve for m, then ask ourselves what do we need in order to sub in the formula, and then that's how we'll proceed. So if you want to find m and it's a bending problem, then you need to write the expression for bending moment in terms of m divided by I is sigma divided by y. Okay, so in order to solve for n, which is the unknown, we need to figure out the other 4 things there, or 3 things there, right? So let's try getting all those things. So first of all, what is sigma? Sigma seems to be, so sigma comes from some strength parameter. In this case, it looks like we need to use the ultimate strength and the factor of safety to find sigma. So the relation between factor of safety is the allowable strength divided by allowable stress. Something we covered, I think, in chapter 1, right? So the strength in this case is the ultimate strength. The allowable stress is sigma, which is an unknown, and of course we know n. So 3 is the factor of safety. SU is 60 ksi. Sigma is unknown, and so we can solve sigma to be 20 ksi. Okay, so we're done with one thing. Next, next is y. So y is the distance from the neutral axis or the central axis. Now, in this case, it's very easy to see that the centroid is pretty much the center of the annular region, right? So we don't have to do any calculation. As I said, the maximum stress will occur where y is maximum. So clearly, it's going to be at the topmost surface. So y would be 5 divided by 2. Okay, so that's the second part is taken care of. Okay. Last thing is the inertia. Now the inertia is the inertia of the rectangular region minus the whole, right? So what we can do here is we can do what is known as superposition to figure out the inertia. We can think of this cross section, sorry, this the cross section of the annular region consists of 2 things. One is a big rectangle which fills the outer region of the rectangle. So let's say that this, I'm going to shade this up to show you that it is actually hollow. So it's this minus the inner part. So if you find the inertia of the first one minus the inertia of the second one, you pretty much find the inertia of the composite section. So this is I1 minus I2. And so all we need is the dimensions of 1 and 2. So you can see that dimensions of this are 5 and so the bigger length is 3.25. So 3.25. Here we have the smaller length. So here it's going to be, so it's going to be 5 minus 2 times the thickness, because the thickness appears here, it appears there. So the thickness is 0.25. So this is going to be 5 minus 2 times thickness. So 5 minus 0.5, so 4.5. And then this is also going to be 3.25 minus twice the thickness, which comes out to be, I think, 2.75. So the inertia is 1/12. Again, the same formula for rectangular. It's basically the width times the height cube. So width is 3.25, height is 5, so cube of that, and then minus 1/12 the width, which is 2.75, and the height is 4.5 cube. Okay, remember everything there is in inches, and so the units of inertia, area moment of inertia is always inch raised to 4 or meter raised to 4. So it's going to be 12.97 inch raised to 4. So now we have effectively found the inertia, and we are set to find the moment. So moment equals sigma, which is 20, divided by, let's see. So I need to multiply sigma with I and then divide it by y. 12.97 and divided by y, which is the height, and this is the maximum height. So it's going to be 2.5, 5 divided by 2. This comes out to be 1038 kip inch. Again, kip is kilopound. Yes, I think that's right. That's right. Good catch. Okay, the last part is to find the radius of curvature. The radius of curvature is 1 divided by the radius. And that's actually from another expression we wrote down involving E and R. So let's just do that. So we have M divided by R equals E divided by R equals sigma divided by Y. Now you could use any two of those. You could use the first part, or you could use the second part to do the computation part. What I normally recommend is don't use the first part, because if your M computation is wrong, then your 1 divided by R computation is also going to be wrong. So just use the second part, just because everything else there is given. So 1 divided by R equals sigma times R. So sigma is, I think, 20 KSI. E is given to be, it's 10.6 times 10 raised to 6. So y is 5 divided by 2. And so if you find that, so that comes out to be, let me write this down. I think people don't know about curvature. Curvature is the inverse of the radius. is 110.4 feet. Okay, so you can see that the curvature is really is a really big value. It's 110 feet. Is it right? Huh? Yeah, I think it's incorrect. I think that's R. I think it should be 1 divided by R because it just doesn't come from that. Hold on. 20, let's do it here. 20 times 10 raised to 6, that's KSI 2. And now you need to, no, my bad. I think I computed R. It should be 1 divided by R. The radius should be a really big value because if the bending is, if it bends a little bit, then the radius would definitely be a very large value. So the curvature should be really small. 12.97. Okay, so what's the unit? So on top we have sigma, it's in KSI, and then E is in PSI. So I think I need to convert that. It should be 10 raised to 3. And the answer should come out in inches. It's 1.45 times 10 raised to -4. But everything we used here was in inches. Oh, sorry, inch inverse. Right? Because it's the units are going to be 1 divided by R, and R has units of inch. Yeah. 7.55. You got 7.55. Is that it? Times 10 raised to 4. Okay, so you might be right. So, okay, so probably that's right. Okay, so really when you do these calculations, at least for the course, if you get it wrong, the final answer, we are not so much concerned as much we are concerned about getting the equations right. But clearly, if you're doing a design calculations, you want to double check, triple check so that you're right. So don't worry about this in the exam because it's time pressure, but and we are going to stress on the your thinking and how you write the equations down and what we put there. Okay. Okay, one last question, and we are question. Yeah.
So can you briefly explain why the y value, the 5 divided by 2, doesn't correlate to the geometry? So like why is it divided by 2 in all cases?
Yeah, so sure, yeah. So any you have m divided by r equals sigma divided by y. Okay, so sigma equals m y I. Okay, so usually what happens in any problem, you're given the moment, right? You're applying a force on the element, and then what happens is you find the moment. So m is given, I is a property of the section, and then the question is, you want some random object of cross section, and let's say that the neutral axis is here, and then we measure things from here. So let's say that this is y1, and that's the max, and here it's y2. So this formula here is telling you that the maximum stress sigma is going to be for a given m, given I, it's going to be where y is maximum, right? So in this case, so clearly it's going to be 0 here because y is 0. So now you have two choices. You could put y equals y1 or you could put y equals y2. So if y2 is bigger than y1, then clearly sigma will be max when y equals y2. And that's what you'll do. So any geometry, no matter what it is, you just figure out the maximum distance and use that to compute the maximum stress. That's what the equations tell us. The maximum stress is always going to be here. So if the beam in this case breaks, you're going to be concerned about this part and not so much about, so if it fails in bending, then it's going to fail at the extreme ends and not at the inner side. So you should use that reasoning to figure out the maximum y. So in this case, this is perhaps a good example where you have a non-uniform body. And we're going to do a problem now where we have a non-uniform body. So here is the next problem. Okay, so this is a T section. So beam shown is acted upon by moment M. Determine the maximum tensile and compressive stress on the beam. So one thing to note here is once this bends, it's going to bend in this fashion. Right, because the moment is as shown. And so what we see is that the top part is clearly going to be in tension. And the bottom part will be in compression. So we need to find the maximum. So we figured out which is tension, which is compression. We only need to find the stress. Okay, so for this particular geometry, we do not know the centroid, right? We need to find the centroid. I don't know, it might be here somewhere. So once we find the centroid, that's how we measure the distance. So our first goal is to find the centroid. Once we find the centroid, we'll use the formula M divided by R equals sigma divided by Y. And then for max tension, we'll use the distance from neutral axis to this part. And then, so that let's call that Y1. Sorry, it should be sigma equals M Y1 divided by I. And for max compression, we'll use sigma equals M, let's call this Y2. So that's all to it. So you just have to figure out, we know, we don't know the centroid, we don't know I, we know M, it's given to us 3 kilonewton meter, and then Y1 and Y2 unknown because we don't know the centroid. So let's find the centroid first, and then find I, and then Y1, Y2 are kind of easy. So how do you find the centroid? Well, let's draw the geometry and choose an origin. This is probably a review of how to find centroid of composite sections. So let's say that this is Y, this is X, this is my 0, 0, and that's arbitrary. I just chose it to be that way. You can choose anywhere, 0, 0 to be anywhere. So what I do is I need to find the centroid, which is probably somewhere here, is guessing, is going to be, so it's going to be the x coordinate, right? So C is equal to summation A times y divided by summation of A. So when I say summation of AY, I'm going to break this down into two sections. One is this. So that's, let's say A1, and then find its centroid. I'm going to use a different notation. I already used 1 and 2. So let me use 2 and 3, 3 and 4, 3 and 4. So A3, Y3 plus A4, Y4 divided by A3 plus A4. Okay. So what are these areas? The area of 3 is, the dimensions are on top. It's 90 times 20. And the centroid of the first part from the origin is going to be 20 divided by 2. So it's going to be 10. Plus the second piece is 40 in height and 30 in width. So 40 times 30. And its center from the origin, okay, always from the origins, this height. That's going to be 20 plus, I believe 40 divided by 2. So 20 plus 40 divided by 2. So that's my numerator. The denominator is going to be 90 times 20, noting that this is the area. And then the other one is 40 times 30. Okay, so when you do the math, comes out to be 22, which is saying that the centroid is slightly below. So this is 20. So it's slightly below that. So it's 2 millimeters below below this, where this section ends. Okay, so now once we know C, we can find Y1, which I said is the distance from this point all the way to the top. So this is (22), and so Y1 you can see is 22. That's right, yeah. And then Y2 is this, is going to be 40 minus 22, which is going to be 18. That's right. 38, my bad, 38. So Y1 is 22, Y2 is 38, and then I need to find I. Yeah, I'm running out of time. Okay, so let me finish this next time. I want to really do this computing I slowly, and yeah, we'll continue on Friday. Okay, so why did we use Y1 for tensile and Y2 for compression? That's because for the given M, when you load it this way, the top part will be under tension and the bottom part will be under compression. It just depends on how this M is. We are substituting the inertia in the formula. We are always computing the inertia about the centroid or the neutral axis. So the neutral axis is right here. And we want to find the inertia about C. I think it's called C bar. Now, I don't know if you recollect this, but if you want to find the inertia about an axis which is not passing through the centroid, then there is a theorem called parallel axis theorem, which we need to invoke. So this is a recap, something we might have learned in the previous class. So if you have a general planar body and there's a centroid, we need to find the inertia not about C, but a different point. Let's call that O. Okay. So this distance is D, and this area is A. So IC is moment about, or say inertia about C. IO is inertia about O, and that's the one we need to find here. So there's a theorem called parallel axis theorem. It states that the inertia about O is inertia about C, where C is the centroid plus the area of the plane element times the distance between C and O. So D is as shown there. And that's how you can find the inertia about O. So this is not something new. You probably have learned this in a course before this. So let's find the inertia about C. So in order to do that, we again break it down into two bodies. One is the top part, the horizontal part of the beam, and then the vertical part of the beam. So we'll find the inertia of both those things. So here's how we'll do it. Take this. Let's call that C1. You want to find it about C bar. And then we have the bottom part. Its inertia about C2, which is its centroid, and then inertia about C bar. So we can say that IC bar equals, let me put the dimensions there for you. So the width of this is 30 mm. The height is 40, and this one is 20 and 90. And then we need to find the distance from C bar to C1. So since I think it's C bar was found to be, let's go back and see what C bar was. C bar was 22. So it was 22 from the top. That's all I need. Let's go back. So this was 22 millimeters from the top, which means this distance between C bar and C1, this distance is going to be, I think, 2 plus 10. Right? I think this is 12. And then we need to find the distance from C bar to C2. So we know that this is 2. Okay, so this one is 2. This one is unknown, but that seems to be like 40 minus, so 40, 20 is the distance of C2 from the top. So it's 20 minus 2. I think it's 18. Okay, so we're all set now to write the inertia. The inertia is of about C bar is, so the formula is 1/12 base times the height cube. So 1/12, the base is 90 mm, which is this, and then the height is 20, the cube of that, plus by the parallel axis theorem, it needs to be the area of the horizontal part. So the area is 90 times 20. And then the distance from C bar to C1, which is 12. So 12 square. Other D. This is the first piece for the left part. For the right part, we have again 1/12 base, which is 30, in the height, which is 40. So 40 cube plus the area of the vertical part of the T. So that's 30 for the width and 40 for the height. And then the distance from C bar to C2 is 18. This is A, sorry, A, my bad, square. This is T. So plugging all the numbers in, what I got was for inertia about C bar is 868 times 10 raised to 3 millimeter raised to 4, which I can convert to meters. 868 times 10 raised to -9. See, so yeah, meter raised to 4. Okay, so we got the inertia. We are all set to find the stress. I believe I wrote it down here. See, let's copy this. Okay, so M equals sig M divided by I equals sigma divided by Y. So let's find the tensile stress. That will be sigma. Let's use the suffix T for tensile stress. That'll be M, which is given. So M Y1 divided by I. In this case, I is IC bar, the one which just found. The inertia, the moment is 3 kilonewton meter. So 3 times 10 raised to 3. Y1 is 22, but that is millimeters. So 22 times 10 raised to -3. Inertia is 868 times 10 raised to -9. So all that comes out to be sigma tensile equals 76 MPa. Compressive stress. Is IC bar the same as IO? No. Wait, let me just clarify this. So here, This is inertia about C1, which is this point, and this is inertia about C2. And IC1 is like IO. What is IO? IO is something I wrote down here. It's the, oh, sorry. There's some confusion about my own notation. So IC1 is like IC, and IC2 is like IC, and then IC bar, which is this point, is like IO. That's right. So it is IO. Sorry about the confusion, but yeah, the comment was absolutely spot on. It's the same as IO. Okay, let's do the compressive stress. Let me indicate that with sigma C. And let me just put a negative sign because it's compressive. The other way people put a compressive sign is because the convention is, they have a convention that y is positive one way and negative the other way. That can be used to figure out the sign convention. So minus m y2 divided by I c bar. No, it's the same inertia which figures out there. However, the y is different here. So m is 3 times 10 raised to 3. The y2, which is this now, is 38 millimeters. So 38 times 10 raised to negative 3 divided by 868 times 10 raised to 9. And sigma c is 131. Yeah, question.
Why you should use
Yeah, that's a good question. So let's go back. In this case, it's just based on the fact that I know that this is, I know for the fact that this is compressive and I put a negative sign, but the way this sign convention goes is, if you look here, the moment, they don't have an axis, but it is counterclockwise. So m is positive, and then usually the top y is positive and down is negative. Now there will be a conflict if, well, so what happens is m is positive here and y is positive up. So the tensile stress comes out to be positive. And clearly, let me just write it down. Okay, so here's how you will figure this out. So draw a specimen, and this is how the moment acts. And let's call that z. And this is y. So y cross z is x, so it should be, x should be like this. Okay, so our convention is this is positive because CCW. So by this formula, sigma equals m divided by I equals sigma divided by y. And so you have sigma equals m y I. So I is always positive. Now it's only m and y which give us the sign. So in this case, here m is positive because it's counterclockwise, y up is positive, and so sigma tensile is plus m plus y divided by I. So it's positive. If m is positive, y is downwards, Okay, it's going to be negative because the convention says that negative is downward is negative, and so sigma compressive is m positive m minus y I, so it will be negative. If you flip the moment, right, it instead of being counterclockwise, it was clockwise. M1, what will happen is you will choose M1 is negative because it's clockwise. Again, y will be the same. Y upwards is positive. So sigma, so on the top face, now you will have compression. So you'll have sigma compression is minus m plus y I. So this is the top face. And then the same reasoning applies for down. So so downwards on the bottom layer, you'll have tension. So you'll have sigma t equals minus m minus y. So when I say minus m minus y, I'm just, there's some value given to m, and I'm just plugging it in that equation, bottom face. So all checks out in terms of sign. It's all consistent. Okay. Any other questions?